Hello. In today's video, we're going to be talking about chapter 14. We're going to be talking about lecture 9. We're going to talk about our first learning objective in this video. So we're just going to be looking at what's called a reaction mechanism. Within a reaction mechanism, we're going to look at what's called elementary steps, and those elementary steps are going to combine to form our reaction mechanism and combine to form our overall reaction. So from our elementary steps in our reaction mechanism, we'll also look at how to determine our rate law and relate it back to our actual reaction. Okay, so a reaction mechanism itself is a series of elementary steps. Okay, so mechanisms are what we would call a pathway for a reaction. So it could be the possible sequence of events. And I say possible because this is a theoretical mechanism, so they're never proven. However, there are things. This reaction mechanism is based on evidence. So mechanisms are based on our experimentally derived rate law, so when we take those concentrations versus rates, we can get our rate law, and then from that rate law and other things, we can come up with a mechanism of what's going on. Okay? It's also based on experimental evidence. So, of course, our rate law itself, what our reactants are, what our products are, and a lot of times they can actually do different techniques during the reaction to find things that are formed for seconds or milliseconds or even less time during the reaction. And then, of course, chemical knowledge. So certain things react in certain ways based on what type of substance they have, or what type of substance they are, and what they are reacting with. So some chemical knowledge is always going to be part of developing these reaction mechanisms. Okay? So with our reaction mechanisms, we have what are called elementary steps. So our elementary steps are steps that are the breakdown of the reaction mechanism. So each step within a mechanism is called an elementary step. Okay, so these are the simplest reactions within here, so they cannot be further broken down. So they are showing what is actually occurring. So they occur as written. So actual collisions going on that occur during the reaction. Again, this is theoretical, but using this chemical knowledge we have, we can say, okay, we think that this elementary step is these two molecules colliding and reacting to produce this. Now, there are 2 or more elementary steps in a reaction mechanism, and those elementary steps are going to sum up to give us what is our overall reaction, what we generally see. So our overall reaction is our chemical reaction. So what you guys have looked at so far. Okay. Now, unlike our overall reaction, we can use our elementary step to determine our rate law. Using the stoichiometry of that elementary step, because we're actually showing with the elementary steps what collisions are occurring. And in this class, we're going to use the rate laws of our elementary steps to determine our overall rate law, right? It's in actual experimental conditions or experimental settings, they use the rate law to determine the elementary steps. But in this class, we're going to use the elementary steps to determine our overall rate law. Okay? So, we already talked about this. Let's keep going. Let's look at what a reaction mechanism would look like. So here is a reaction mechanism. We have 2 elementary steps. Those elementary steps sum to produce an overall reaction. Okay, so let's look at some things here. So here we have N2O2, or say NO2 reacting with NO2. So we have 2 molecules of NO2 reacting. And when they react, so when they collide together, they produce NO and NO3. Okay? Then NO3 and CO react to produce NO2 and CO2. Okay? Now, if we look, NO3 is produced in this reaction and then consumed in this reaction. Okay? Anytime we have something that is produced in one reaction, then consumed in another one, we call that an intermediate. Okay? So this is something that doesn't actually show up in the overall reaction, but it is part of the reaction mechanism. Okay? So, when we combine these are going to cancel out. Our intermediates will always cancel out. And then, actually, in this case, one of our NO2s are also canceling out to give us an overall reaction that is NO2 gas plus CO gas produces NO gas and CO2. Okay? So we will always produce our overall reaction using our elementary steps. Okay? So this would be considered a 2-step mechanism. And we see some important things with this. 1, the intermediate. And 2, it shows what we call molecularity. So what things are actually reacting and how many. Okay, so first let's look at our reaction intermediate. So a reaction intermediate is a compound that only exists in the elementary steps, not in the overall reaction. Our elementary steps, our reaction intermediates, a lot of times are actually seen in some sort of technique during the reaction, so they have proof that these intermediates exist, but not always. Okay, so they are going to be produced in one elementary step. So first they're produced in one elementary step, then they're consumed in another subsequent elementary step. So they're produced, then consumed. Okay? So here we produce it, and here we consume it, and it is nowhere in this overall reaction. So that would be an example of an intermediate. Now, here we show that we are reacting 2 molecules of NO2. Here we are reacting NO3 with CO gas. That amount of molecules that are in elementary step is what we call molecularity. So this is going to be a classification of elementary steps based on the number of reactant molecules in that elementary step. So if we have 1 molecule, we call that a unimolecular, 2 bimolecular, 3 termolecular. So this is showing how many molecules are colliding at one time during an elementary step. Okay, so this is still collisions, right? So unimolecular happens on occasion. Bimolecular is usually the most common. So 2 things collide, they react to produce a product. Termolecular is going to be rare, and it's because it's really hard to get 3 molecules colliding, 3 different molecules colliding all at the same time. So it's going to be the most rare of the types of molecularity, and it's going to be the most that we can get reacting at one time. So termolecular is kind of the maximum amount of molecules we can have reacting with each other all at the same time. Now, as I said, we can base our rate law on our molecularity. So if we have one thing reacting, it would be a first order process, so first order elementary step. So it would be K times by the concentration of A. If we have 2 molecules colliding, so a bimolecular process, we can either have 2 of the same or 2 different molecules. If we're 2 of the same, we are a secondary process where it is secondary overall and secondary with respects to one substance. If we have 2 different substances, we are going to be a second order process, but we're going to be first order in both reactants. If we have a termolecular process, here we have either 3 things, 3 of the same thing reacting, 2 of one thing and 1 of another, or 3 different molecules reacting together, giving us a third order process, either third order overall and third order with respects to one reactant, third order overall, second order with one reactant, first order with the other, third overall, first order with each of the reactants. So using this idea of molecularity, we can determine our rate law for an elementary step. And that's because these are the collisions that are actually occurring, or Theory has it. So these are the molecules that theory tells us. So they're actually occurring. So it makes sense that if we have something that is secondary with the secondary process and they are both with the same substance, as we double its concentration, we can quadruple its rate, right? Because now we have twice as many around. It only depends on that one substance, so twice as many, we get quadruple the amount of reactant. Okay, so all of this is based on collisions. What's colliding, what concentrations are going to affect it. Okay, now we can take our rate laws from our elementary steps and actually take them and determine our overall reaction rates rate law. So to do this, we first have to figure out what type of, or what substance, or what elementary step is our slowest. So the overall rate law is based on the slowest elementary step. That slowest elementary step, we call that the rate determining step. It determines our rate because it is the slowest one, right? Every other process is going to occur very quickly, so it won't stop the reaction from going, right? It's that rate determining step, or slowest elementary step, that determines how fast or slow a reaction is. It doesn't matter any of the rest of the elementary steps. Whichever one actually slows us up will be our rate determining. So when we are writing our rate law for our overall reaction, we have to write it only in terms of reactants. So this is a note. Rate law for the overall reaction must be in terms of reactants only. So we can have no intermediates. Okay. So how do we do this? How do we write an overall rate law based on a mechanism? Well, the first thing you need to do is you need to determine which is the rate limiting step. It will be really easy. The steps will be labeled as slow or fast. So it'll be the slow step. All other steps will be labeled as fast steps. So generally these will be labeled, so it'll be really easy to determine which one is our rate determining step. Next, we are going to write our rate law. Write rate law in terms of the rate determining step. Excluding, or really only in terms of reactants. So if we have our first step as our rate limiting, it is really easy. So rate law equals rate law of first step. There will be no intermediates we have to worry about if the first step is our rate determining step. If any other step is our rate determining step, we have to change any intermediates into reactants. So if we don't have our first step being our rate determining step, we must express intermediates in terms of reactants. So I will go over an example of each of these so you guys can better understand what exactly I'm talking about. Okay, so here we have a multi-step reaction with an initial slow step. So since our slow step is our first step, really easy. We're just going to write our rate law for this step. So the rate law for our first step is rate is equal to K1 times by the concentration of our reactants, which is NO2 squared, because there's two NOs. Now, in order to write this as an actual rate law, you'd just write rate is equal to K NO2 2. So this would just be converted into K. So whatever your K value is, K1, K2, or any craziness in between, it'll convert into K to form our overall rate law. Super easy, right? Until we get to a first step that is slow step. So if we have a fast step as our first step, it makes it much harder. So first thing we need to do is we need to determine our slow step, which is this one, and we're going to write our rate in terms of that slow step. So rate equal to K2 N2O2 H2. Now, what you hopefully notice is that N2O2 is an intermediate. So, by the way, is N2O. So, because this is an intermediate, we have to rewrite it. So, in order to rewrite it, we need to first find where it is formed. So, this is a reaction where we form N2O2. So, we can use it in order to determine or to rewrite N2O2. So, we're going to take this equation. Now, hopefully you see that this is a reversible process, and hopefully you note that since this is an equilibrium, the rate of our forward reaction is equal to the rate of our reverse reaction. Okay, so those rates will be equal because it is an equilibrium process. So we could say rate is equal to K1 NO squared, or rate is equal to N2O2. We can then set these rates equal to each other, which gives us K1 NO2 is equal to which is equal to K minus 1, so I forgot K minus 1, N2O2. Now, I want to replace that in my equation, so I'm going to put that on one side of my equality and put everything else on the other side. So I'm going to divide both sides by k minus 1. So I get k1 over k minus 1 NO squared is equal to N2O2. So this right here can then go in to there because they are equal to each other. So we would say that our rate is equal to K2 K1 over K minus 1 NO squared times by H2. This gives us rate is equal to K2 K1 K minus 1 NO squared H2. This will all just become K, and we get rate is equal to K NO squared H2, and that is our answer. Right there. Okay. Okay. So, we'll try another example. Let's try this one first. So, using the mechanism for formation of the product K, what is the intermediate? So, whenever you do this, the easiest thing to do is write our overall first. So A plus 2B goes to C plus X. Here, D is produced, then consumed, so D is our intermediate. Okay. Let's try another mechanism problem, as these give people a lot of trouble. So, we've got the following reaction mechanism. We want to determine the overall reaction, identify any intermediates, and we want the overall rate law based on only reactants. So, we have the following reaction mechanism. If we look, we see that we produce I and then we consume I. So we produce two I atoms and then we consume those two I atoms. And then we also produce H2I and then consume H2I. So I and H2I are our intermediates. Okay, so they are going to cancel out. And we'll get I2 plus H2 goes to 2HI. Okay. Now, we want to take this idea and we want to identify our slow step, write our reaction rate or our rate law in terms of that slow step, and then since we have intermediates in that slow step, we need to write in terms of reactants only. So we have, let's just erase real quick. So we've got our slow step. We would write the rate of that slow step as rate is equal to K3 H2I and I. So we do our rate constant K3 times by our reactant concentrations. Then we see that both of these are intermediates, so we're going to have to look at where we produce each of these substances and rewrite them. So let's start with H2I. So we want to solve for H2I. So we're going to use this one right here. So we'd say that rate is equal to K2 H2 concentration times by I concentration. And then in our reverse, since we have an equilibrium process, our rate is also equal to K minus 2 H2I. We can then set those two rates equal to each other and we get K2 H2 I is equal to K minus 2 H2I. We're then going to solve for this, and we get K2 over K minus 2 equals H2 concentration times by I concentration. We can then place this in for this. So we get K3 times by K2, K minus 2, H2, I times by I. And we get rate is equal to K3, K2, K minus 2, H2, and then I, and because there's two of them, it is squared. Now, H2 is a reactant, but I is not, so we still need to rewrite. So now we need to solve for I squared, which not as bad as it seems. So let's start there. We've got our rate is equal to K3, K2, K minus 2, H2, I squared. This is where I is produced. So this is now the reaction we're going to look at to try and rewrite I. So rate is equal to K1 times by I2, and rate is also equal to K minus 1 I squared. We'll set them equal to each other. K1 I2 is equal to K minus 1 I squared. Solving for I squared, we get K1 over K minus 1 times by I2 is equal to I squared. Then this can go in for I squared, and we get rate is equal to K3, K2, K minus 2, H2, K1, K minus 1, I2. Solve for it, we get rate is equal to K3, K2, K1 over K minus 2, K minus 1, H2, I2, and then we just set this whole thing as K, and we get our big rate equals K H2 I2, and that's the end.